So if you type a number next to like a bad AI prompt,
Yeah.
the AI doesn't just read the number. It physically rewires its own attention mechanism on the fly to simulate a reinforcement learning upgrade.
Which is just, yeah, it's completely mind-blowing.
It really is. Welcome to the deep dive, everyone. We are looking at a stack of state-of-the-art generative AI research today. Specifically, we're exploring this really groundbreaking paper titled In Context Learning as Implicit Policy Gradient.
Right.
And as a learner, I'm always looking for those foundational mechanics, like why things actually work under the hood. So our mission today is to uncover the hidden algorithm making this possible and, well, what it means for how you interact with AI.
Yeah, because this paper, it entirely changes how we understand the latent mechanics of these models.
Mm-hmm.
I mean, we already know that large language models can miraculously improve their own answers, right?
Right, yeah.
Like if you just show them previous attempts alongside the scores those attempts received, they get better.
Yeah, anyone who uses OPRO, optimization by prompting, knows this. You feed the model a context window filled with past outputs, give each one a score, like, I don't know, 61 or 78 out of 100, and just ask it to do better.
And it does.
Exactly, it does. But the mystery has always been why, because there are no actual weight updates happening.
Right, exactly.
There's no fine-tuning. The engineers aren't in the background tweaking the code while you chat. So how does handing a text prediction engine a number like 78 cause it to just magically write a better response without being reprogrammed?
And that is the core theoretical breakthrough here. The authors mathematically prove that this score-conditioned in-context learning admits a direct structural correspondence to policy gradient optimization.
Okay.
Specifically, it mirrors the reinforce algorithm, which is, one of the absolute foundational pillars of reinforcement learning.
Okay, let's unpack this because that is a massive claim.
Oh.
In traditional reinforcement learning, you have an agent navigating an environment, right? Like a robot learning to walk. It takes a step, gets a reward or a penalty, and then explicitly updates its internal policy.
Actual code, yeah.
Right, to maximize those rewards for the next step.
Right.
But an LLM in a chat window is frozen. Its weights are completely locked. So how on earth is it executing reinforce?
Right, so it's doing it implicitly.
Yeah.
And the mechanism lies hidden inside the transformer architecture itself, specifically within the self-attention mechanism.
Okay, the self-attention mechanism.
Yeah. In standard everyday language processing, self-attention basically acts as a semantic matcher. It looks at the query and figures out which past tokens are most, semantically relevant.
Like the word bank paying attention to river or money, depending on the sentence.
Exactly. But this paper demonstrates that under the specific condition where you introduce numerical scores, that self-attention mechanism fundamentally shifts its behavior.
Wait, really? It just shifts.
It does. It stops just looking for semantic similarity, and it literally acts as a reward-weighted aggregator. It begins weighting the previous examples by their scores.
Okay, so to use an analogy, it's like a student who isn't just rereading a textbook, but looking at their past 5 graded practice essays.
It's a great way to put it, yeah.
They aren't just blindly blending all those essays together based on like which ones use similar vocabulary. Their brain is physically giving more gravitational pull to the essay that got an A.
Exactly. Pulling their next attempt strictly in that direction.
Pulling it in that direction. Wow.
Yeah, the attention mechanism applies a gravitational pull proportional to the numerical reward. But you have to remember, LLMs are incredibly complex probability distributions.
Right.
If you apply too much gravitational pull toward a single high score, you risk destabilizing the entire model.
Right. Like the student trying so hard to sound smart for that A that they just start stringing together completely incoherent thesaurus words.
Just word salad, yeah.
Yeah, entirely forgetting basic grammar. So if the model chases the score blindly, why doesn't the output just devolve into degenerate broken text?
Well, because of a built-in mathematical safety net, the researchers derived what is called an exact pathwise KL bound.
Okay, KL bound. Let's break that down for the listener because it's crucial. KL divergence basically measures how much one probability distribution differs from a reference distribution, right?
Precisely. In plain English, the model operates within a trust region.
A trust region.
Yeah. When the attention mechanism shifts the probabilities of the next word to savor the high-scoring example, the KL bound mathematically restricts how far that internal distribution can shift in a single step.
Oh, I see.
It forces the new output to stay somewhat anchored to the model's original pre-trained understanding of language.
So it's basically saying, yes, steer toward the 95-point essay, but do not violate the fundamental laws of English syntax to do it.
Exactly. It prevents the AI from going completely off the rails in a single leap. It guarantees stable, iterative improvement, which is, a hallmark of good policy gradient algorithms.
Okay, I have to push back here, though.
Sure.
Because math on a whiteboard is beautiful, theory is pristine, but real multi-layer LLMs with complex softmax attention are incredibly messy.
Well, absolutely, they're chaotic.
Right, they are dense webs of billions of parameters.
Yeah.
So does this actually hold up in the wild? Because my immediate skepticism is this. If the model reads a brilliant essay with a 95 next to it, is it actually using the number 95 as a mathematical weight? Or is it just a massive pattern recognition engine that recognizes inherently good writing through semantic analysis, and it's basically just ignoring the score entirely?
See, that is the exact right question to ask, and the researchers anticipated this exact skepticism.
Okay, so what did they do?
To prove this empirically, they didn't rely on tiny toy models. They ran these experiments across a massive roster of state-of-the-art models. We're talking Llama 3, Olmo 3, Qwen 3, GPT-4o, Gemini 2.5, and Claude Sonnet 4.
So they basically tested the entire heavyweight division of modern AI.
They did.
Yeah.
And to answer your pushback about whether the model is just recognizing good text, they designed the ultimate control. The shuffled score experiment.
The shuffled score experiment?
Yeah, they took the in-context examples and completely randomized the scores assigned to them.
Oh, wow. Okay, so a factually incorrect, terribly formatted response might randomly get a 95.
Yep.
And a brilliant, perfect response might get a 20.
Exactly. Now think about your hypothesis. If the model was just reading the text for semantic quality and ignoring the numbers, the shuffled scores wouldn't matter.
Right. Because it would still produce a great answer by just emulating the high-quality text.
Exactly.
But I'm guessing that's not what happened.
Not at all. When they shuffled the scores, the correlation between the provided scores and the model's output probability changes dropped to near zero.
Zero.
Specifically, 0.01.
Wow.
Yeah, this is causal proof. The LLMs are reading and utilizing the explicit numeric values, not just inferring the text quality.
That is wild.
Yeah, if you give a completely garbage answer a high score, the attention mechanism will physically pull the next output toward that garbage answer.
It is literally doing implicit math with the score token on the fly, just overriding its own semantic judgment of the text.
And what's fascinating here is that this capability scales directly with the size of the model.
Really?
Yeah, when they analyzed the data, the larger models, like the 70 billion parameter version of Llama 3, showed the absolute highest correlation between the scores and the probability shifts.
Okay, so the bigger the brain, the better it is at this hidden score weighting game. Why do you think that is?
Well,
Is it because a 70 billion parameter latent space just has more dimensions to map abstract numerical hierarchies compared to like an 8 billion parameter model?
that's definitely the most likely explanation. Larger latent spaces just allow for more specialized attention heads to form during pre-training.
Right.
They have more capacity to dedicate specific pathways to abstract concepts, like numerical weighting, without cannibalizing the pathways needed for basic language generation.
Makes sense.
Furthermore, the researchers found a fascinating physical constraint. The magnitude of this distribution shift decreases as you add more examples to the context. It perfectly matches a theoretical 1n scaling curve.
Okay, 1n scaling. So as n, the number of examples goes up, the pull of any single example goes down.
Correct.
Let me see if I have the mechanics of this right. This happens because of how self-attention normalizes itself, right, through the softmax function.
You're right on the money. Walk us through it.
Okay, so self-attention operates on a finite budget. Every time it generates a token, all the attention weights looking back at the context have to sum to 100% or 1.0. So if I give the model just 2 examples, those 2 examples are splitting a massive chunk of that attention budget. The mathematical pull of a score on one of them is huge.
Right.
But if I give it 32 examples, the denominator in that softmax function gets massive.
Yep.
The attention budget is stretched incredibly thin across all those tokens, so the incremental influence of any single score just gets squashed.
Exactly. The model's finite weighting budget gets diluted, which is exactly how gradient descent behaves when you increase the batch size in traditional machine learning.
Oh, wow.
Yeah, it's another point of proof that this is a true optimization process.
Okay, here's where it gets really interesting. Now that we know the model absolutely reads the scores, and we know it's a structural shift governed by attention budgets, Where is this happening inside the neural network?
Right.
Like, if you think of an LLM's layers like a massive complex assembly line, where does the score inspector actually sit?
That takes us into mechanistic interpretability, which is essentially neuroscience for AI.
Neuroscience for AI, I love that.
Yeah. To find the score inspector, the researchers developed a metric called the Score Extraction Index, or SEI.
Okay.
They use this to sift through the thousands of individual attention heads across the models, looking for the ones uniquely specialized for extracting score information.
Wait, how do you even index an attention head for something that specific?
They used a technique called linear probing. They essentially trained a tiny, simple classifier to look at the internal activations of the different attention heads and see which ones could reliably predict the value of the score token.
Oh, I see.
So if the classifier could accurately read the score just by looking at a specific attention head's output, that head got a high SEI.
And they found them. These specialized mathematical score reader heads actually exist.
They do. And the most revealing part is that they aren't scattered randomly. Linear probing showed that this score extraction happens almost exclusively in the late layers of the model.
The late layers.
Yeah. For context, Llama 370B has 80 layers in its architecture. The maximum correlation for score processing peaked way at the back at layer 68.
Layer 68 out of 80. Okay, think about that assembly line analogy again. The prompt enters layer 1. The early layers are basically just figuring out raw syntax and basic grammar.
Right.
The middle layers are building semantic meaning, context, logic. The car is fully built, the engine is in, and it's rolling down the line.
Exactly.
And only at the very end, at layer 68, does the score inspector step in with a clipboard and say, all right, based on the numerical scores of the past examples, steer the final steering wheel exactly 3 degrees to the left.
It's a brilliant architectural division of labor. The model preserves its language generation capabilities in the early and middle layers and applies the policy gradient steering only once the semantic representations are fully formed.
That is so elegant.
But they didn't just stop at observing this. To prove it wasn't just a correlation, they performed a causal ablation.
A causal ablation, so essentially an AI lobotomy.
Precisely. They went into those specific late layers, right around layer 68, and they zeroed out the hidden representations exactly at the positions of the score tokens.
Wow.
Yeah, they specifically suppressed the attention heads that had a high score extraction index.
Okay, let me guess. If you blindfold the score inspector at layer 68, the whole illusion falls apart.
Yeah.
Even though the numbers are still technically in the text prompt, the model loses the ability to weight by them and just reverts to treating the prompt like standard semantic text.
That is exactly what happens. When they suppress those specific high SEI heads, the model's ability to weight by score sharply dropped. In Llama 370B, they saw up to a 42% drop in the score probability correlation.
42%.
Yeah. The model essentially forgot how to do reinforcement learning. This causally proves that those specific late layer heads are the physical engine of the in-context policy gradient.
That is incredible. I mean, it is so incredibly rare to find the actual physical mechanism inside the black box. Usually we just observe the output and guess, but here they found the exact gear that turns the math.
It's a massive milestone in interpretability. And, to put the final indisputable nail in the coffin, to prove this is truly mimicking the reinforced algorithm,
Right.
they did a head-to-head comparison.
Okay.
They measured the directional shift of the model's output probabilities using this in-context score method and compared it to taking the exact same model and doing an actual explicit one-step reinforce fine-tuning update to its weights.
Wait, so they compared the no-code just type numbers in the prompt method against the hard-code engineer-level weight update method?
Yes, exactly. And they measured the cosine similarity of the resultant probability shifts.
Okay, for the listener, we need to contextualize cosine similarity here. In a vector space with billions of dimensions, which is what a 70 billion parameter model is, 2 random vectors are almost certainly orthogonal.
All right, yeah.
Their cosine similarity would be essentially 0. Finding 2 vectors that point in the same direction in a space that massive is incredibly difficult. Anything above, say, 0.05 is usually considered a strong directional signal. What was the similarity score here?
The similarity score they found was over 0.45 across all model task pairs.
0.45. That is massive. In a high-dimensional space, that means they are practically identical twins. They are holding hands and walking in the exact same direction.
Exactly. This mathematically proves that both methods are shifting the model's output in the exact same direction. The in-context prompt isn't just a clever trick. It is literally triggering a simulated fine-tuning step inside the network.
Okay, so knowing how this assembly line works, how does a listener actually use this? On a practical level, if someone listening right now is setting up a complex prompt for a coding task and they want to trigger this implicit policy gradient, does the formatting of the numbers matter?
Formatting matters immensely. The researchers tested multiple ways of representing the scores.
Okay.
If you use decimals like 0.82, percentages like 82%, fractions like 80, 20, 100, or explicitly say 82 points, all those work remarkably well. The specialized attention heads at layer 68 easily recognize them as quantitative weights.
What if I write it out like a human normally would in a sentence? This response scored an 82%,
That introduces severe noise, and the correlation dropped significantly.
which makes total sense if you think about tokenization, right?
Exactly.
LLMs don't read words. They read tokens. 82.0 might be a single, clean token that the model has mapped mathematically, but 82 gets chopped up into weird subword tokens.
Yep. The vectors don't align.
Right. The mathematical vectors don't align as cleanly, so the layer 68 heads have to spend computational effort translating semantic words back into a mathematical weight, and the efficiency of the gradient shift is just lost.
Precisely. You must provide clear, explicit numeric markers. And, unsurprisingly, the no-score control, where you just provide previous outputs without any numbers, fails to produce the policy gradient shift entirely.
And what exact tasks were the researchers testing this on? I know prompt optimization is the standard use case for this.
Yes, they tested it heavily on reasoning tasks. They used the GSMAK dataset for mathematical reasoning and the GRP dataset for reading comprehension.
Okay.
By providing past attempts and scores, the AI successfully optimized its own reasoning paths to perform significantly better on these benchmarks. But, and this is a critical part of the paper, they also tested it on jailbreak prompting.
Jailbreak prompting, meaning intentionally trying to bypass the model's safety filters to elicit restricted or harmful information.
Yeah. If we connect this to the bigger picture, it is vital to impartially relay the researcher's ethics statement here.
Of course.
The authors are absolutely not endorsing harm, nor are they trying to hand out new attack sectors. They used public standardized jailbreak benchmarks to demonstrate a profound underlying reality about these models.
Which is that the math doesn't have a moral compass.
Exactly. The exact same mathematical framework that makes an AI helpful, compliant, and capable of self-improvement also perfectly explains why it can be manipulated into generating harmful outputs.
Wow. Right.
If an attacker provides in-context examples of harmful outputs and deliberately assigns them high numeric scores, the AI's internal attention mechanism at layer 68 will dutifully pull the next output toward that harmful space.
Because to the layer 68 score inspector, a high number is just a high number.
Right.
It isn't reading the semantics of the text. It assumes the earlier layers handled that. It just sees the 95 and steers the wheel.
Yes. The researchers argue that understanding this specific mathematical mechanism is absolutely vital for building robust defenses against adversarial attacks.
Because you can't patch a vulnerability if you don't know where the underlying mechanism lives.
Exactly. By isolating this to specific late-layer attention heads, safety teams now have a physical target to monitor or restrict when trying to prevent jailbreaks.
So what does this all mean? Let's bring this right back to you, the learner, staring at that blinking cursor in your AI chat window.
Yeah.
The biggest takeaway here is that you don't need to be a machine learning engineer to optimize a large language model. You don't need to know how to execute gradient descent. You don't need compute clusters. And you don't need to write code to update billions of weights.
Not at all.
By simply providing past attempts and explicitly pairing them with numerical scores sorted in ascending order, you are doing so much more than just giving the AI context. You are literally hacking the architecture. You are triggering a hidden, highly sophisticated policy gradient optimization right inside the model's late-layer attention mechanism. You are turning a static black box into your own personal dynamic reinforcement learning engine.
And that leads to a rather profound thought to leave you with.
Ooh.
We've just spent this time establishing that self-attention inherently acts as a reinforcement learning mechanism simply by reading annotated context. Currently, our context windows are limited, maybe a few 100,000 or a couple of million tokens. But what happens when context windows become near infinite? Right. Could a future AI, given a continuous, unbroken context window that contains a lifetime of simulated actions and natural numerical environmental feedback, effectively become a fully autonomous reinforcement learning agent?
Just constantly learning.
Exactly. It wouldn't need a training phase and an inference phase. It could run entirely inside its own working memory, constantly weighting and optimizing its policy based on the scores it encounters without us ever needing to update its underlying code again.
It wouldn't just be predicting the next word, it would be evolving in real time purely through its own memory. That is a massive paradigm shift. Something to think about the next time you drop a simple number into your prompt and ask an AI to do just a little bit better.